Hi, and welcome to this part 4 of our lesson 6 video that's all about materials. And today we're going to be looking at polymers. And if we have the time towards the end of the video, we may take a look at hardness testing and tensile testing. A polymer is a really very long and large molecule, but it's the result of the joining of many monomers. They're all identical monomers that join up together to form a specific material. A monomer is one molecule of what we will eventually call a polymer. And those monomers are, generally speaking, for many applications, hydrocarbons. Now, carbon has 4 valence electrons that permit really 4 linking ports with substances like hydrogen. Okay, now hydrogen and carbon, that's my hydrocarbons. And a lot of polymers or plastic materials are hydrocarbons. But you can get even more permutations or types or qualities or all kinds of different kinds of plastics by adding even other things like sulfur, like chlorine, like oxygen, and so on and so forth, that can also be joined into those monomers that will link up in different ways, because as the original monomer gets more complex, well, how they link to the other monomers also gets more complex, and it can create different types of structures. And it's those different types of structures that gives to the polymer quite often its main characteristics. If we simplify everything right down to the bare bones, we can say that we have 2 large families of polymers. We have thermoplastic polymers and we have thermoset polymers. And we can sort of subdivide the thermoset polymers into 2 groups, the true thermoset and the elastomers. The first family, the thermoplastic group, well, is composed of really linear polymer molecules. So monomers that have been grouped or linked end to end to form very long chains. And these chains don't have lateral links. That means that each chain is independent of all the other chains that it's bunched up with. And if I reduce it to popsicle stick form, well, I get a chain that is slightly flexible in its joints depending on how hot it is, but that remains just a single chain. That is why we could use in our little injection molding 101 video that I did, a little quickie video, we used a granular pre-polymerized polymer that was melted and injected into a mold to produce the tree of parts that I wanted to make. And that's why this little Homer guy could be ground up and remolded into something else, because they're linear polymers. They're thermoplastic polymers. Knowing that is important, because that means that we can do stuff to thermoplastics that we wouldn't be able to do on thermoset plastics. So it's important to know what you have. And as an example of what you can do, well, let's get this sheet of plexiglass. And I have my trusty heat gun here. So let's heat up a corner and see if we can deform it. And there you go. Bent, but not broken, not even cracked. We have a really nice form there. And this is really the basis for all that vacuum molding we always hear about. But if I heat up a linear polymer, a thermoplastic polymer, well, I can deform it. But how can that work? Why doesn't it break? Well, it's because of the way that the polymers, the very long chain of monomers, are arranged. If they are excited, they can slip and slide along each other. When they aren't, well, they're pretty fixed in their position, but they're not attached to their neighbors, so we can reposition, once excited, a polymer like this into a new position, and it will, once cooled down, maintain its shape. A good way to look at it is to look at a bowl of spaghetti. But why a bowl of spaghetti? Well, because it's not exactly like a polymer, but it acts in a similar fashion, and it'll help us to understand. And we all know what spaghetti looks like, and if you don't, well, it's time to get out into the world and try new things. If I take a freshly cooked bowl of spaghetti that's still a little wet, and I stick a fork into it and try and pull the spaghetti out, well, some spaghetti will follow the fork and will slip slide and fall off, and more than likely by the time I get the fork well out of the bowl, there'll be no spaghetti on it. That is what's to be expected with wet noodles. Okay, now let's say I let that spaghetti cool for a while. It's going to get a little tacky. The noodles get a little more rigid, and this time if I stick the fork into it and pull it up, I'll get a blob that will follow the fork up. It won't maintain its shape, but it's a little more coherent. However, if you take that bowl of spaghetti and go and put it in the fridge for a few hours, once you take it out, you'll notice that the spaghetti is a lot drier and it's a lot more rigid. And this time, if you plunge the fork into it and pull it out, you're going to get a mass of spaghetti that has a well-defined shape. It's going to look like the bowl that it was in. And that is a lot like thermoplastics. However, you have to be careful with thermoplastics because there's a very fine line between melting a thermoplastic and burning a thermoplastic. So temperature control is crucial if you're going to be doing things like welding, or forming like we did with the plexiglass a few minutes ago. If you overheat a thermoplastic, well, you damage the bonds in the polymers and its properties will be shot. I mean, it's not going to act the way it should, and it's not something that you can fix. Thermoset plastic are rigid and very hard. They cannot be reground and re-injected, or they cannot be reshaped. A good example of that would be the handle on this cooking pot, or the casing of this heater blower. These polymers are exposed to heat, and we don't want them to get soft when they get heated. So we choose a thermoset plastic because it won't soften up when heated. How can that work? Well, thermoset plastics are produced by very long chains of polymers, as was the case with thermoplastics, but chains that have lateral links. Those lateral links create structures that are basically triangulated. And even though each joint in this mock-up is flexible, there still is no play here because of the triangulation. So I get a polymer, yes, that will want to soften up its joints with heat, yes, but that won't because of its mechanical properties, its shape. And that's why we get handles and casings that resist heat. Now it's important to say though that they are not heat resistant as steel would be heat resistant. If I heated this up with the heat gun, I would eventually destroy the handle because it does have quite a low melting point. It's not going to melt, it's going to burn, okay? And as soon as it starts to burn, it's destroyed. So basically my linear or thermoplastic polymers got more flexible and injectable with temperature, whereas these thermoset plastics are going to stay rigid right up to the bitter end and kick the can all at once. And that leaves my elastomers. Now, getting back to this rigid structure, it's fixed in time and space. this pot handle is never going to be anything but a pot handle or some kind of landfill. Okay? And that's true also for this elastic, because even though it is elastic, it is a thermoset type plastic. Now if I break this handle, I can't weld it back together, and that's the same for this elastic. So if I break or cut this elastic, I can't re-weld it together. It is set in its ways. It is a thermoset plastic. However, how does it work? Why is it elastic? Well, that also has to do with its structure. Now, the polymer joints stay flexible, but if I get lateral links that don't create triangulation but are more cubic in shape, well, I get a form that has a certain possibility of movement in it. And that's what elastics do. They just go from a cubic shape to an elongated shape and back again when we remove the tension. Elastomers. The important thing to remember here is that once it's polymerized, a polymer is a polymer and it can't revert back. We can destroy it, we can burn it, we can break it down into its basic components, carbon and hydrogen and whatnot, but we can't remake hydrocarbons out of it. Okay? Now, the question I always get at this point is, what about my granules and my injection molding? I'm not repolymerizing anything there, because I'm taking what is a polymer in granular form, exciting it with heat to just below its burning point and re-injecting it into another shape, but it has never stopped being a polymer throughout that whole exercise. And that leads to the other big question. Well, if thermoset polymers are all that rigid and can't be softened by heat, how do we get to mold a complex handle like that? If you're having a hard time wrapping your head around the idea that we can injection mold thermoset plastics to produce things like the handle on this pot, well, it's probably because you're thinking polymerized plastic. You're not thinking monomers. And that's the trick. Now, when we were injection molding our thermoplastics, well, they were already polymerized. They were already solid, but we could melt them and inject them. And that's not the case with the thermoset plastics. But that's not a problem, because most plastics start life out as a resin, either in powder form or in liquid form. And that's something we all pretty well know. It's just that we don't always realize that we know it. And a good example of that is this. This is a tube of epoxy resin. What we could call a tube of a monomer. Okay? Something that hasn't been polymerized yet. But what am I going to do? Well, I'm going to add a hardener to the resin to initiate an exothermic chemical reaction, and the heat and the reaction is going to produce a polymer. It's going to produce a thermoset polymer. Now, if I took that mix before it had time to cure, but what we should really say, before it had time to polymerize, and injected it into a mold and let it set or become a polymer inside the mold, well, I would have injection molded a part in thermoset plastic. Some monomer resins can be injected into molds and use hardeners to initiate reactions. Great, but there's some that don't even need a hardener. They're just polymerized by heat, and in that case, well, we can just inject the monomer into a mold and heat the mold, and we'll have our polymerized part. Some monomer resins come to us in powder form, and when that's the case, they're often shaped and polymerized by compression molding. With compression molding, we take the powdered monomer and pack it into a mold. And then the part that comes from that mold is cooked. And that polymerizes it and gives it its permanent shape. That compression molding technique is very popular with thermoset plastics because it gives us a lot of control over the moment of polymerization. There's even monomers that want so much to join that we use blockers to retard the moment of polymerization. And that's the case with these silicone rubber type gasket materials. They are injected as monomers with another ingredient that once evaporated, well, leaves the road clear for the formation of long chains. And once it's polymerized, well, obviously it's permanent. Extrusion is also a way to give shape to polymers. And a good example of extrusion, well, is a hot glue gun. It's really a mini extruder, and we're extruding a thermoplastic mass through a die opening that gives it a shape. In this case, it's just used for glue. But what's odd is this mini extruder uses something that comes from a much larger extruder, and that is the glue gun stick itself. Now, this was produced by extrusion. Extrusion can also be used to produce pipes, like this ABS plumbing pipe. And if I extrude a pipe made of elastomers and cut them at widths, well, I make elastics. And if I use extrusion to extrude a pipe down vertically, in other words, in the sense or the direction of gravity, while it's still hot, clamping that pipe between two half molds and injecting air into it, well, I'll have performed what's called a blow molding operation. And that's how we get a lot of these containers. I can even extrude sheets like this sheet of plexiglass, and it might look like I'm holding nothing, but it is the sheet of plexiglass. There we can see the reflection that I bent the corners up on to show how it becomes more plastic with heat. But this sheet plexiglass is an accurate material, and to get that size accurate, the thickness, well, the sheets are extruded fine, but then they're laminated for that final sizing before they get too hard. So we can do some accurate parts with forming and extrusion. And if you have a sheet of a thermoplastic material that you can heat up, you can place on a die and suck the air out from between the sheet and the die, well, you'll have performed a vacuum molding operation. And that's how we get a lot of our bubble wrap packaging. Now, if in this process you use the suction of the vacuum and a positive pressure on the top to assist, probably because there's a lot of deformation required on a thick part, you want some real power, well, you'll have something that both blows and sucks. Polymers are really best put into shape by forming or molding operations, but they can be machined. And as a general rule, I like to divide polymers or plastics up into two groups as far as machining goes. The first would be the softer thermoplastics, the ones that are like nylon. And the second group would be the hard thermoplastics, like plexiglass, and the thermoset polymers. Those are a lot more brittle and don't machine exactly the same way as the first group. So let's start with the softer thermoplastics. Here's a little piece of nylon, and I would consider this to be in the first group as far as hardness goes. This has a soapy feeling to it. It's rigid, it's hard, but it's really not all that hard. And you can feel it just by touching it. So this would be what I would consider to be a softer thermoplastic. And for these softer thermoplastics, we're going to want really positive cutting tool angles. So on the face where the chip is formed, we want a nice positive angle. So positive cutting angle on the face of the tool. And we want a lot of clearance, and we want large tool nose radius. We really need very, very sharp tools for cutting this type of polymer. As far as speeds and feeds go, I would recommend to slow things down a bit. Most people cut plastics way too fast as far as rotation goes, but also as far as feed goes, because we have a tendency to feed as fast as we can, and that is really problematic. A good, slow, controlled feed is the way to go. So I would recommend for most applications a depth of cut that needs to be quite reasonable, because remember, these materials are grabby, so you need to have good rigid setups or else you're going to get into trouble. So not too much depth of cut, but as far as feed goes, I would keep it slow. On the lathe, somewhere between 3 and 6 thousandths of an inch per rev. And remember, we really need sharp cutting tools and large tool nose radius for this type of plastic. As far as rotation goes, well, I recommend about 150 surface feet per minute for your RPM calculations. And remember that if you're going to be deep hole drilling or slotting or grooving deeply into a part, friction creates heat, and heat equals melting plastic, and that's a real problem for deep hole drilling and deep grooving. So remember, coolant is allowed. Now, very few people use water-based coolants on plastics because they seem so easy to cut, but they're very, very easy to melt. So those water-based coolants will really help out a lot as far as giving you a better finish, but not melting things onto the tool. Cutting polymers really isn't that different from cutting metals. It's just that everything's a lot softer. That first group, the soft thermoplastic group, well, was very soft, and as far as cutting goes, it resembles a bit like cutting a very soft brass. The second group, however, is a lot harder, and if we apply the same logic that we've been applying to metals, well, this second group, the main difference is that we're going to want to use neutral cutting angles because it is a little harder. But remember, that second group had two different types, the thermoset plastics and the harder thermoplastics. Well, the harder thermoplastics, like Plexiglass, are still going to give you continuous chips because they do get malleable and ductile with heat. But our thermoset plastics, like the handle on a pot there, like this one, well, is going to give you powdery chips, and the cutting action resembles a lot the cutting action that you'd get with gray cast iron. So we can see the similarities there. Now, for the second group, we want neutral cutting angles and smaller tool nose radius. But the cutting speeds and feeds, well, it's pretty well the same for both groups. Since they are a lot softer than most metals, polymers quite often are a bit of a chore to hold onto a machine. So if you're holding a block on a mill with a finger clamp, well, you'd be best to put a pad under the clamp to increase the surface of contact between the two and to hold the part a little more positively. The same idea goes if you're holding a block in a vise. Don't hold it by the very edge. Make sure that you get it as deeply into the vise as possible. Maximize your surface of contact. And that's true for the lathe as well. 3-jaw or 4-jaw, you're holding on thin strips. So if you can, avoid 3 and 4 jaws and opt for clamps or collets like this, since they really increase the surface contact between the tool and the part. It'll hold it a lot more positively. A few little things before we wrap this up. And the first is fillers or strengtheners. Now you have to know that a lot of polymers incorporate strengtheners, and those are physical things that help with properties that the polymer just doesn't have a lot of. And the best example of that would be a polymer resin and fiberglass, what we call fiberglass. Now the resin is a thermoset resin or a polyester, but the fiberglass is glass fiber and it's incredibly abrasive. So if you try to machine that, you're going to be getting yourself into trouble. I'm not saying you can't drill or cut fiberglass, but it really reaps havoc on your tools. And there's not just that, there's straight up fillers. I mean, some polymers incorporate wood fiber, some polymers incorporate even minerals to lower their cost. And these are very abrasive materials that again will really wreak havoc on your tooling. So be aware and be careful of those things. And the last thing has to do with something that a lot of people have difficulty with, and that's drilling plexiglass. Drilling plexiglass is difficult because we get a lot of cracking, and that's due to two major things. The first is the feed. A lot of people, when things are cutting well, tend to push even harder on the handle, and that's a big no-no. You want to feed at a reasonable rate regardless of how easy things are cutting. Feeding any faster, well, will create a lot of stress on the part and will start those micro cracks forming. The second is the cutting angle. Now, helical drills have positive cutting angles. So if you don't have straight flute drills for drilling polymers, well, maybe you should use your helical drills, but grind a small flat on the cutting lip to make it act as if there was a neutral cutting angle on this tool. Okay, so helical drills are positive, positive angles grab, and for plexiglass that's a big problem. So grind a little flat on your cutting lips, and here's a picture of what that could look like. I mentioned at the start that at the end of the polymers I'd add on a short section on materials testing if we had the time. Well, this video is starting to get a little on the long side, so I think we'll push back the material testing to a little quickie that'll come out in a few days after this one. So, as I usually say, have fun, be safe, and happy machining.
There you go.